So we've encountered the two-sum problem, and we've also encountered the two-sum number 2, the sequel, and then now we've gotten another sequel in the sum series, and this is the three-sum problem. So in this question, we want to find 3 numbers in our input array that adds up to 0. So unlike the previous questions, we don't have a target. The target is always 0. And instead of finding 2 things, we want 3 things now. And also, another thing that's different is that there are more than one valid answers. You see in this list, there are 2 pairs of valid answers. Alright, so another thing that's changed is that the output should not contain any duplicate triplets. What does that mean? So looking at this one example, yeah? So there are actually 3 sets of triplets that work. So the first set is -1, 0, and 1. These 3. And the second set is 0, 1, and -1. So 0, 1, and -1. But if you kind of lay them out, they're kind of the same thing, right? It's the same thing, it's just kind of reordered funny. We don't want any duplicate triplets. And then the last one is of course -1, 2, and -1, which is completely unique than the previous ones, okay? So that's the question. How do we go about solving this problem? We can start with the caveman solution. If we just write 3 nested loops, and then we just Unga Bunga test every possible triplet combination, I think we can find all of the triplets because we're literally just trying every combination, right? So with this kind of code, this is going to be O of n3, right? Terrible, of course. But another consideration that we have to do is that, like before, where if we have this, -1, 0, and 1, like this, we might find a separate triplet, this, 0, 1, -1, which are basically the same thing, and they're duplicates. They don't use the same index, but their values are the same, and we have to like deduplicate it somehow. So how would we even do that? So back to this triple for loop. So I'm just gonna say like if nums I plus nums j and plus nums k, and that adds up to 0, then we have to do something here. Okay, this is the case where we found a match. We have to deduplicate it somehow. So if I have this combination, I would have to sort this thing. Well, it's already sorted. And then I would have to turn this into a tuple. Why am I turning it into a tuple? Because I'm gonna have a set. See, this set is gonna keep track of all of the unique entries, all of the unique triplets that we have so far. And as you know, entries, keys of a set need to be immutable. So that's why we have to convert it to a tuple. So once we have this, we can just slot it in, shwink, -1, 0, and 1. And then next time, if we encounter like these 3 instead, 0, 1, and -1, I would have to sort it so it's in the same order every time, and then I'd have to turn it to a tuple, and then I would have to insert it into the set. And if there's already something that exists here, then nothing would happen basically. And at the end, I would have something like this, and then I'd have to turn this back into the list of lists format that the question wanted. It's kind of troublesome, but it works. And you know, running this algorithm to do the deduplication, basically constant time. Because all the operations we're doing here, like the sorting, turning it into tuples, and then like putting it in the set, this is all operations done on like exactly 3 elements. So it'll be like 3 log 3 plus 3 and whatever. Basically, it's all constant time. So it's pretty good. All in all, Unga Bunga caveman method kind of works. It's just that the time complexity is n to the power of 3. Yeah, the solution kind of stinks. So what about another method? Well, if you're taking inspiration from the original two-sum problem, we did use a hash map for that. So let's just apply the same concept in this 3-sum problem. So the first thing we do, we have to turn it into a dictionary where the key is going to be the value, and then the value is going to be the index. We're going to create a value to index mapping. -1 can be found in index 0, 0 can be found in index 1, 1 can be found in 2, and then once we hit -1, it's probably going to replace the 0, right? And then something like this. And then we can do a for loop, a double for loop this time, just 2, I and j. So instead of looping through the array a 3rd time to find k, we can say that if we have nums I, which is any arbitrary first number, and nums j, any arbitrary second number, and the one that we're looking for right now, the nums k, if this adds up to 0, this means that if we want nums k, it's gonna be minus nums I minus nums j. So let's have a look at a more concrete example. Let's say through this process of a double for loop, let's say I found an I over here and a j over here. So like here, if I substitute these values, then the number that we're looking for is minus nums I, which is minus minus 1, positive 1, minus 2, so minus 2. So we're looking for a minus 1. So this number, instead of looking for it in the array, we just kind of yoink one and see if it exists already. And turns out it does. Very cool. And then that'll be O1. So what this will be O of n square for time complexity, and then we'll need this dictionary for the space complexity of n. And also we have to run the same deduplication steps from the Unga Bunga solution. But unfortunately, I do have some bad news for you. And said bad news is this. You should aim for a solution with O of n squared time and O of 1 space, where n is the size of the input array. So my friend, that doesn't even work. We cannot use a hash map. So if we can't even use a hash map, then what are we supposed to do? Actually, now that I think about it, I don't think the hash solution ever worked at all in the first place, disregarding that it's using extra space, which is not allowed. If we have an example like this, so clearly there are no matches here. There's no universe where this would ever add up to 0. But if I were to do the hash solution, then it would create a hash that would look like this. And then let's say I do my double for loop. I have an I here and a j here. And according to our formula, nums k, the number we are looking for, is equal to negative this plus negative this. So negative 2 plus negative negative 1. So that's a positive 1. So we're looking for a minus 1, right? Makes sense. So if you have a 2 minus 1, then to complete the set, we need a minus 1. So then it'll look for this minus 1 in our hash map. And then it'll say, oh, look, there's a minus 1 here at index 1. We can use that for the third number. So then we end up using the same index twice. So like this solution is just all kinds of messed up from the start. Well, my friend, it's time to take inspiration from the two-sum, the second one, right? And that was the one where you had a sorted list and then you're using 2 pointers to find the matching pair. Well, if you haven't solved this problem, then I recommend that you solve it first. I also have a video in the description. So we know that the 2-pointer solution for this problem only works because the array was sorted. So within the same principle, we also have to sort our input array to use the 2-pointers algorithm. And also, since we're gunning for O of n square, we can feel pretty guilt-free about using a sort, because a sort is just n log n, which is smaller than the n square. So how do we apply this? So we'll take the original input array again, and then we're going to sort it. So we have this. And since we need 3 values, remember how like in the hash map solution, we have like 2 for loops, and then we basically use the hash map to find the third value? What if we employ a similar idea, but instead of that, we're going to use 1 for loop, and then we're going to use the 2-pointers algorithm to find the other 2 values. I'll have a pointer called I, which I'm going to call the anchor pointer, because this is the one that's going to be responsible for going through every element one by one. And then I'm going to create a left and a right pointer, as usual, just as we would in a 2-pointer solution. So now we just do 2-pointer things. So we're going to add up all of this, which will give us minus 3, which is too small. It's smaller than our target 0. So we have to increase the L to the right? And then we repeat this process. Well, again, these 3 are the same numbers, so they're going to add up to minus 3 once again, which is again too small. I'm going to move this here. Negative 402, that's going to add up to minus 2, which is too small. And then I'm going to move it here, which is negative 1. Still too small, unfortunately. We have to increment L here. And now L and R are both pointing at the same index, which means that the 2-pointer search for this iteration is over. We didn't find a successful triplet using this anchor. So let's move the anchor. We're going to move I here now. And then I'm going to put L here and R here. Now, the reason I'm not putting L here is because, as you can see, negative 4, negative 1, and 2. This is a combination that we've tried before. So when we move the anchor, I am initializing L to 1 unit to the right of the anchor, because otherwise then we would be testing something that we've already tested. There's just no point. And then here, so we can see we have minus 1, and 2. Hey, look at that. We actually added up to 0. That's great. So you found a match. And then we can just put it inside our little results array. Ooh, you might be thinking like, what about like duplicates? Do we have to like deduplicate this? Well, the answer is no, we don't. You don't have to do that. Why is that? Okay, that's because since this array is in a non-descending order, let's say there's like another minus 1 here, right? And let's say there's like another 2 here. Just like, wait, let me make it nicer. Negative 1, 0, and 2, 2. So let's say we found this pair. Very good. Added it here. And then we increment these 2. And then we use this again. Oh no, we can actually write checks to avoid this. So what we can do, since we know that we use the minus 1 as our success, we don't want to use another minus 1 for L anymore. Nope. L is going to keep moving to the right and see that, oh, actually, that's another -1. I don't want to use that again. Because if I use -1 and -1 again, the last value, no matter what, has to be 2, right? The last value has to be 2, which means we're going to once again insert a duplicate triplet. But if L is different, let's say L is like, for example, 0, this would mean that we would want an R of 1. Hey, and this is a different triplet, you see? So the anchor can stay the same, that's fine. It's just that once we find a matching triplet, we cannot reuse these numbers again. We need to find new numbers. So that's why when we find a success case like this, we want to skip over all of the values that's the same as what we just used. So we just used -1. Let's just skip over all of it and go to the first new value. And same thing for R. For R, I just used the 2, so I'm going to skip all the 2s. So that's just going to jump right here, you see? And here, we're lucky in that we find a unique pair. So -1, 0, 1. That's another combination, and that goes straight here. -1, 0, and 1. So at this point, we don't know that it's over yet. Then we have to increment our anchor. So our anchor gets moved here, and oh, if you notice, this anchor is the same. Now the question is, do we have to skip over all the -1s, all the anchors that we've used before or not? The answer is yes, because we're just going to end up finding the exact same triplets again. -1, 0, 1, -1, -1, 2. So that's why we also skip these over. Zoink. Our anchors here, our L and R starts here once again. Just to finish it up, we have 0, 1, and 2. This adds up to a total of 3, which is bigger than 0. We're going to move R down here because it's too big. We have 0, 1, 2 again. Well, oh, here, another question that I wanted to ask is that you notice that I kind of read the same value twice on our failure cases, but we skipped it in our success case. Why is that? Well, actually, truthfully, you can also skip this as well. You can write the while loop to skip it or whatever if you really want to. But the thing is, even if I read 0, 1, 2 and 0, 1, 2 and it fails twice, it wouldn't affect my result. If you want it to be a bit more performant, it's probably better to just skip it, but I think having so many while loops is a bit ugly. You'll see the code later. It's already pretty ugly. Just because there's so many edge cases. And then once we realize that it's too big, we're going to move R once again to here. And then now they're both pointing at the same index, which means that we've kind of searched everything here already. Then we increment I here. I, L, R, same thing. No answer here. Way too big. R gets moved here. That's it. That's the end. And then for the I, we can't really move it up anymore because like if I move I one more time here, I'm going to put an L here and like where the fuck am I going to put an R? Like it's done. So I only goes up to here, like 2 elements before the end. So just to recap, when we're going to be writing the code, I want to keep in mind that we have to skip same values of I, and we also have to skip L and R on success cases, right? All duplicates. For the time and space complexity, we're going to have an anchor I that's going to loop through every element, and for each index I, I'm going to be running the 2 pointers algorithm, which is an O of n algorithm. So looping through every element, that's O of n, and then doing the 2 pointers on the remaining elements is going to be another n. So in total, it's O of n squared. For the memory, we're not using any extra memory. Very cool. O of 1 memory. And that fulfills the requirements we had earlier. Let's get to coding. So first up, we're going to sort the array, nums.sort. Next up, we're going to create a result. And then we have to define our anchor. Remember we named it I earlier? For I in range of length of nums minus 2. We'll only run this until I reaches like the third last element. And then we stop. And then I'm going to define the L and the R. L is going to be 1 unit to the right of I, the anchor. And then R is always going to be starting at the end of the array. So now that that's settled, I want to write a while loop. And this while loop is just going to do the 2 pointer search. So while L is less than R, I'm going to say that total is equal to nums I plus the number on L, the number in L, and the number in R. Okay, so if total is less than 0, right? Remember that the total has to add up to 0 for it to count. If it's less than 0, then it is too small. It's a negative number. It's too small. We need to increment L by 1. Otherwise, if it's too big, then R has to be decremented by 1. And then for the last case, this else case is when we get a hit, where total is equal to 0. So that's pretty simple. We're just going to append it into result. Nums I, nums j, and nums k. And then before we return the result, we kind of have to increment L to the next value and decrement R to the next value, and then we return the result, right? this definitely works, but this does not deal with the duplicates at all. So let's write the code for that. So we can't just like stupidly increment this by 1. We have to write a while loop, yeah? And what I'm saying is nums L plus 1, the number to the right, is nums L, okay? So if we just succeed it, and then the number to its right is the same as the current number in L, then that's not acceptable. We want to skip over it. L plus equals 1. And then similarly, while nums R minus 1 is equal to nums R, we want to decrease this by 1. So what's this going to look like? So that means if we find the same triplet again, -1, -1, and 2, 2 here, and this succeeds, then it's going to run the while loop, and it's going to ask, hey, is this next value to the left of L the same as L? Well, the answer is yes. So we want to increment it by 1. So L's here. So if there's another -1 here, it's going to do the same thing. It's going to ask one more time, hey man, is this value to the right the same as my current value? If yes, then I'm going to move L over here. And then it does the same for the right side. Once we're done with this one in the initial match, it says, hey, is the value to my left the same as this value? And the answer is yes. Then we move R by 1. And then here, the answer is no here. See, because 1 is different from 2. And same thing here, 0 is different from -1. So it stops here. So you notice that in this while loop, we're stopping at the index right before the number changes, right? So actually, for the next loop, we kind of have to increment one extra time to move it into the index that we want. Which is why after we do the skips here, we need one extra push at the end. Now this to me, to be completely honest with you, looking at this condition is a little bit of a code smell. The reason being is that this is a recipe for an out of index error, because you're grabbing the value to the right of L, assuming that L is not the final element. There is a chance that L is like on the final index, and then you cast this, and then it's going to throw an error, right? So we need a guard for that. And the same thing for here as well. You might be trying to access like the index -1. Just to prove it to you, we already got an index out of range thing here. So, you know, we got to put a guard. So I'm going to say that if L is the second last element, right? Second last element, not the last element, the second last element, then we stop there. And the reason why I only let L go to the second last element is because here we're going to increase L by 1 no matter what. So it's going to go to the last element, right? So same thing here with R. I'm only going to let R go up to 1. Because if I let R go to 0 and then it runs R minus 1, then it's going to go grab the -1 value, which is not what we want. And also, one other edge case, holy shit, there's so many edge cases that we have to deal with, is when we increment our I or anchor, we have to do the same skipping thingy. But luckily, it's a little bit easier to write. So if I say if nums I, if we were to come around to the next iteration and then we realize that the value at this current I is the same as the previous value, means we don't want to check this anymore. So I'm going to say continue. Right, then I just want to skip it over. But we don't want to skip if I is 0. So we only want to skip if I is greater than 0. So remember this was our guard, right? So let's say I is 0 in this case, right? So it's going to be I, L, and R, right? But in this case, we haven't done the L and R stuff, so we don't care about that. So what this is saying is that without this thing, it's saying that if nums I, well, aka nums 0, is equal to nums 0 minus 1, so -1. If this and this are equal, then skip this iteration. I is going to go here. This algorithm's not going to execute. And then the output, which was supposed to be like this, now becomes like this. So that's bad. That's why we need this if I greater than 0. So let's try again. Yay. Woohoo. Look, I'm going to be real with you, man. This has so many gotchas. Like if you're like coding this live, this is a little bit of a gotcha. Remembering to skip over the anchor is also a little bit of an edge case. And then even the writing the code to like skip over duplicate elements, paying enough attention so that, you know, you have to add like one little step at the end, you know, because the skip thing only takes you to like the latest duplicate, but not the new number. And then having this guard as well, because like this might cause an out of bounds exception. It's just like a lot of edge cases. So definitely a good problem to practice, to be like super attentive of like how anything and everything could go wrong. All right, that's it. Okay, bye.